notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos. I am hoping that by September 2024, I will have all 32 videos ready from section 1, number theory and computation, but it looks like I will run a little late with that. But then in October 2024, the 13 to 15 or so videos for consumer arithmetic, and then on should be back on schedule. November 2024, sets, December 2024, measurement, January 2025, statistics, February 2025, algebra, March, relations, functions, and graphs, April, geometry and trigonometry, and May, by mid-May, vectors and matrices. As you already know, I have divided section 1 into 32 videos, but since I missed one, that would be 33 videos, all of which will be made available on YouTube in their entirety. That is the 33 videos from section 1. This section forms the foundation on which the rest of the syllabus is based. How well you can handle this section will predict how well you will do with the rest of the syllabus. Please make sure you view these 33 videos and learn them well before you continue onto the other sections. We finished these 16, and we are now at scientific notation, video 24. As I said, somehow I had overlooked objective 10 in this position here. That was the last video that was done. So this objective says, write any rational number in scientific notation. And the example that CSEC gives is 759,000. That's the standard way we would write that number. But as scientific notation, it would be written as 7.59 times 10 to the 5th power. That is what we will be learning about today. So write any rational number. So let's remind ourselves what rational numbers are again. We talked about natural numbers in section 1. Natural numbers are the counting numbers, 1, 2, 3, 4, and so on. Then you have whole numbers are those counting numbers including 0. So whole numbers. Beyond that, you have the integers, which includes the negative whole numbers. And then you have the rational numbers, which now includes fractions. So any rational number, any number that can be located anywhere here, we should be able to express any number here, any rational number, as scientific notation. So we said rational numbers, not irrational numbers. So first of all, we need to know what is standard form, what does it look like. Then we need to be able to express floating point numbers, that's the one you are accustomed to using, as standard form. And while this objective does not call for this, we will reverse the process and express standard form or scientific notation as floating point. So what is standard form? In science, sometimes you need to write extremely large numbers or extremely small numbers. Here are two examples. This number here, 602 with 2 and a whole lot of zeros behind it, is known as Avogadro's number, and it is the number of units in 1 mole of a substance. So that's an extremely large number, Avogadro's number. But then you have this other number here, which begins with a 0.000, a whole bunch of zeros, and ends up with 9109 kilogram, and that is the mass of an electron. This is an extremely small number. So there must be a convenient way of writing those numbers than the way you see them here. It is more convenient to write those two numbers as 6.022 times 10 to the 23rd power, that's the one at the top, and 9.109 times 10 to the negative 31 kilogram. This is what it looks like. How convenient if you could write it like this, than like that you may forget one of the zeros or put in an extra zero, or like this rather than that. Let's deal with numbers greater than 1. Consider for a moment the number 2,800. That can be rewritten as 280 times 10. It is the same number as the one in the front. Or 28 times 100. Or 2.8 times 1,000. Or 0.28 times 10,000. Those are different ways of writing this same number. But then this 10, this 100 here, this 1,000 here can be compressed. So we can rewrite that as 280 times 10 to the first power, or 28 times 10 to the second power, or 2.8 times 10 to the third power, or 0.28 times 10 to the fourth power. Now we will choose the one that has only one significant figure on the left of the decimal point, followed by a times 10, and then you have a power to it. So which of these follow that pattern? 2.8 times 10 to the third. Now, remember that because this is the format that the scientific notation is written in. Let's deal with the number less than 1, and we will end up with something very similar. 0.0028 is 0.028 divided by 10, or 0.28 divided by 100, or 2.8 divided by 1,000, or 28 divided by 10,000. Now let's deal with the 10 here. We will express those in index notation. So 0.028 divided by 10 to the first power, 0.28 divided by 10 to the second power, 2.8 divided by 10 to the third power, and so on. But dividing by 10 to the first power is actually multiplying by 10 to the negative first power. So we will change that division now to multiplication, and we get 0.028 multiplied by 10 to the negative 1. Remember, all of those are the same thing. 0.28 multiplied by 10 to the negative 2. Those are three ways of expressing the same thing. So now we will choose the one that has only one significant figure on the left of the decimal point, followed by times 10, and then the correct power. In this case, if the number is less than 1, you will get a negative index. So let's look at those two again. 6.022 times 10 to the 23rd power, that's for a number greater than 1. And 9.109 times 10 to the negative 31, that's for a number less than 1. So if you look at them again, 2.8 times 10 to the third power, 2.8 times 10 to the negative third power. That one is less than 1. This one is greater than 1. As the name suggests, remember we are trying to understand why is this kind of notation called standard form or scientific notation. As the name suggests, standard form has a standard format. So you have a whole number part followed by a point and then a decimal part times 10 to either a plus or minus index, where I is an integer from 1 to 9, inclusive. D after the point represents a decimal fraction, which may or may not be present, and the index n is an integer, meaning it could be positive or negative. So it has a standard format. So you notice this format, 6.022 times 10 to the 23rd, or 9.109 times 10 to the negative 31. That is the format scientific notation is written in, sometimes called standard form. And remember, we just discussed how we came up with 2,800 can be expressed as 2.8 times 10 to the third power. And also how 0.0028 can be expressed more conveniently as 2.8 times 10 to the negative third power. What you see on the slide here and here was to explain how you move from a floating decimal point notation to standard format or scientific notation. There is a much easier way. Now, if you find this video useful and interesting, please like and share. That is, like and share. And you may also consider subscribing to this channel. It doesn't cost you anything, and it does mean a lot to me. So now that we understand what standard form is, or scientific notation, let's learn how to express floating point numbers, that's the numbers we are accustomed to, as standard form. It's not that difficult. All right, so now we are going to learn how to express floating point numbers, that is the type of number we are accustomed to writing, to standard form. We are going to deal with numbers greater than 1 first. So let's look at this number. It's a fairly large number. We want to carry it to standard form, correct to 2 significant figures. So first of all, we will move the point from where it currently is to the left, such that there is only one non-zero digit on its immediate left. That is to the position between 6 and 7. We want to move it and put it here. So only one non-zero digit will be on the left of the point. Now, once you get that, you count how many places you move that point and express it as times 10 to the n, and n being the number of places you moved it. So in this case, we moved it 3 and 3, 6 and 3, 9. So we would write times 10 to the 9th. Then secondly, you would round off the number with the point in the new position to the required significant figures. And you would write that on the left of the times 10 to the 9th. So our point is here. And we want 2 significant figures. That's 1, 2. By now you know how to do this. Your answer would be 6.8. That will be to the left of the times 10 to the 9th. And so this is your standard form. 6.8 times 10 to the 9th. From now on, you would hear me say exponent instead of times 10. Let's look at another example. You want to carry this number as standard form, correct to 1 significant figure. So by now, you understand there is a point here, even if you don't see one. You move it to the left until there is only one non-zero digit on the left of it. So that would be 3 and 3, 6 and 3, 9 and 1, 10. You have to put it between the 2 and the 6. So you get times 10 to the 10th. So our point is here. Let's round off what we have here, whatever we have here, to 1 significant figure, that is at this point. So 2.6789 rounded off to 1 significant figure, and you get 3. So the standard form for this number that you see up here, the scientific notation, is 3 exponent 10. That means 3 times 10 to the 10th power. Next example, 9 million as standard form, correct to two significant figures. First thing, we move this point from where it is such that there is only one non-zero digit on its left. That will be 3 and 3, 6. So we write times 10 to the 6th power. Then we round off here with a point in a new position to two significant figure. That's 1, 2, and so we get 9.0. Remember, in one of those, when we had to round off numbers to significant figures, and we couldn't because the zero caused some problems. This is the format that we can use, and you can clearly see two significant figures there. That was example 3. Example 4, 15.00, a standard form, correct to one significant figure. Well, we move the point one place, so that would be times 10 to the 1. And we round off, the point is now here between the 1 and the 5. We round off at that one position, and we get 2 times 10 to the 1, but normally you don't write a 1. Normally, this is not done with small numbers. Only large numbers are carried to scientific notation or standard form. Next one, 1.20000. Now we are dealing with numbers between 10 and 1. And this is not normally done either. So the point is already there. You don't have to move it anywhere. So it is 10 to the 0. And then you want to round it off to three significant figures. That would be 1, 2, 3. So it would be 1.20 times 10 to the 0 power. But 10 to the 0 power is actually 1. So actually, you are writing back 1.20 now instead of 1.20000. So this is not done with small numbers, as I said. Now let's deal with numbers less than 1. This is 0.000000463. So that number is extremely small. You want to express it as standard form correct to two significant figures. That this number is less than 1, I think you will understand with me that you would have to move this point to the right until you only have one digit on its left. And instead of using a positive index for the n, you will use a negative index. So you move the point from where it currently is to the right, such that there is only one non-zero digit on its immediate left. That is to the position between the 4 and the 6. Count how many places you have moved that point and express it as times 10 to the negative n. In this case, it would be times 10 to the negative 8 power. So the point is here. You will now round off the number with a point in new position to the required significant figure and write that on the left of the times 10 to the negative 8. So we want two significant figures. That would be, that 4 will be 1, that 6 will be another one. Remember, these zeros are not significant. So you get 4.6 exponent negative 8. Next, we want to express that number as standard form, correct to two significant figures. By now you know, you move that point until you only have one non-zero digit on its left. And in this case, we just moved it 5 places, but the index is negative 5. So negative 5 or negative index indicates a number that is less than 1. Positive indicates a number that is greater than 1. So the point is between that 6 and that 0, two significant figure. This is 1. That's the next one. You look at this one is 8. So you know what to do with that by now. And that becomes 6.1 exponent negative 5. 6.1 times 10 to the negative 5. Let's look at another example. Express that as standard form, correct to three significant figures. So we move the point from where it is to the right and your index would become a negative index. So that's times 10 to the negative 2. So the point is between the 1 and the 4. It's no longer there. Those 2 zeros don't count. So it's 3 significant figures. 1, 2, 3. This is a 5. That 2 becomes a 3, and we drop everything there. So we get 1.43 exponent negative 2. So that is how you convert any rational number into standard form. Any rational number. So let's briefly look at converting the standard form back into floating point notation. This is actually doing the reverse of what we just did. So you know that if the index in the standard form is positive, that the number is greater than 1, and that if the index is negative, that the number is less than 1. So we don't need to spend much time on this. 5.6 exponent 10 to the 5. This is a number greater than 1. So you will move this point 5 places to the right. That 6 will take up 1 of the space. So you will add 4 zeros behind the 56. So if the index is positive, move the point that many places to the right, adding zeros as may be required. And if the index is negative, move the point that many places to the left, adding zeros as they may be required. So this number we were looking at just now, it is positive. We will move this point 5 places to the right, but that 6 will take 1 of the space, so we will add 4 zeros. This index is negative, so we will move the point 4 places to the left. That 2 will take 1 of the place, so we will get 0.000, that is 3 zeros, 245. 1.7 exponent negative 7. To carry that to floating point, we will move the point 7 places to the left. But remember that 1 will take up 1 of the space, so you would add 6 zeros after the point. 0.0000010. 6.023 exponent 23. That 0 will take up 1 of the space, that 2 will take up 1 of the space, that other 2 will take up 1 of the space. So you will write 6, 0, 2, 2, and add 20 zeros, like that. 4.87 exponent negative 3. You will move that point 3 places to the left. This 4 will take up 1 of the place, and so you'll get 0.00487. 7.4 times 10 to the 6th power, 7.4 exponent 6. Because this is positive, that number is greater than 1. So we will move this point 6 places to the right. The 4 will take up 1 of the space, so we will add, after 74, 5 zeros. 2 and 3, 5. All right, let's see how well we learn that. We want to express this as standard form correct to 2 significant figures. So we will move the point 3 and 3, 6 and 3, 9. That means we will get a times 10 to the 9th power. You have a 4, so the point is now between the 4 and the 5. You want 2 significant figures, 1, 2, and so your answer is 4.6 exponent 9. Next one, this number here, it's less than 1, 2 significant figure. We move the point 3, 4, 5 spaces. So what do we get? 10 to the negative 5th power. We want 2 significant figures. That 5 will be 1. This 4 will be the other one. This don't count. So you get 5.4 times 10 to the negative 5th power, or 5.4 exponent negative 5. Now we go the other way around. We have the standard form. We want the floating point. This is positive. So this number is larger than 1. We have to move this point 8 places to the right. So we will get how many zeros after the 391? 6. 391, 60. All right, 2.41 exponent negative 6. That means that this number is less than 1. We will have to move the point this way 6 places. So we will write the 241, and between that and the point you would add 5 zeros. 5 zeros. Next one, 7.63 exponent 4. That number is greater than 1. So you need to move the point to the right. So you write the 763. The 63 will take up 2 of the places. So you just need to add 2 more zeros. Next, this number, we want to carry it to standard form, correct to one significant figure. So the point is here. We can see the point this time. We move it 3 and 3/6 places such that there is only one non-zero digit on its left. And so we get times 10 to the 6th power. We want one significant figure, so we are going to have to round off at that position where the 7 is, which gives us 8. 5.2 exponent 4. This number is greater than 1. So obviously we will move the point to the right. So you have the 52. This 0 takes up one of the places that we need to move the point, and so we have to add 3 zeros. Next one. Okay, we have this number. It is much smaller than 1. We have to move the point from where it is until it comes between 3 and 4. Always one non-zero digit on the left of the decimal point. That is part of why it is standard form. So we move it 3 and 3/6 and 1/7. So we get times 10 to the negative 7. 2 significant figure. Remember, these zeros don't count. 3, that's 1, and 4. So your answer is 3.4 times 10 to the negative 7. Now this one is standard form. Let's carry it to floating decimal. You have a positive 12 here, which means that the number is much greater than 1. We have to move this point 12 places to the right. The 9, the 4, and the 3 will take up 3 of those places. So that leaves us with 9 zeros. And finally, this number, correct the 2 significant figures as standard form. Remember, if you don't see a point, it is understood that the point is on the right of the far right digit. So the point is here. We move it 3 and 3/6 and 1/7. So you are going to get times 10 to the 7th power. 2 significant figure. 4 is 1. That place where that 0 is the second one. This digit over here is 5. So that 0 becomes 1. And you get 4.1 exponent 7. Okay, so we did a little more than what the objective requires. Note, if you are not told where to round off the scientific notation, use all the digits from the first to the last non-zero digits inclusive. For example, if you have this, you will use those. Leave out all trailing zeros or all leading zeros. So section 1, objective 11 completed. And that brings us to the end of this video on objective 11, section 1.